Hello ladies and gentlemen, welcome in a new video. This video is about cooling cycles again, and in this video we're going to discuss the efficiencies of a cooling cycle, and we're going to discuss how a real cooling cycle would look like. Since in the previous lecture we talked about an ideal cooling cycle, so now we'll discuss what's different in a real cooling cycle. So over here, just to make a recap of the previous lecture, I have the cooling cycle. There's an evaporator in which the most important process takes place, the process which really consumes energy. So the process by which we can remove heat is the evaporation process. We've got a throttle valve to make this evaporation process possible. Over here we got a compressor to increase pressure so we can get rid of our heat which is in the cycle a little bit easier. And over here we've got, of course, heat coming out. Over here we have the TS diagram of this cycle, and at the end of this video we're going to discuss how this would look like for a non-ideal cycle. But first I want to talk about the efficiency. Since it would not be really fair to talk about efficiency for a cooling cycle, we usually talk about the coefficient of performance of a cooling cycle. Coefficient of performance. And the way in which this coefficient of performance is defined is usually by dividing the energy required dividing this by the required input. So this is how we usually calculate the coefficient of performance. And for a refrigeration cycle, it would look like this. Coefficient of performance for a refrigeration cycle looks like, what is the energy required? Well, the energy required, what a refrigeration cycle actually, what we want to do is, let this be the cycle. So just to make sure that, so this is the cycle, and in this cycle goes energy Q cold, in from a cold region, so for instance in the inner side of your refrigerator, so from a cold region, and out comes, actually it's waste heat, but in some cases it can be used efficiently to, for instance, heat the city or whatever, if you're talking about industrial refrigeration processes. Comes Q hot out, and usually it's just waste heat, so to a hot region. And this is the process, and this process requires some work. So in our case it is the work that we put into the compressor to keep the process going. So our energy required, what we actually want to do is remove heat, so that would be the Q cold in. That's actually what we want to do. We want to remove heat. The required input, what we have to do by ourselves is add some work. So actually here we are. This is the coefficient of performance for our refrigeration cycle. In order to calculate the Carnot efficiency, we have to regard the process as a Carnot process, and the most ideal process. And a Carnot process looks like this in a TS diagram. We have two temperatures, T cold, so lower temperature, and we have T hot, higher temperature. So this would be the temperature at the back of your fridge, and this would be the temperature in your fridge. And then we have this process, just use another color. Use this process over here. So here the process goes, and it's really simplified. But here we have stages 1, 2, 3, and 4. And this is as ideal as it could be. And it's reversible. And here we have the energy coming out, Q hot out. And here we have the energy coming in. And in our case, this Q cold in. And it operates between two temperatures, T cold, T hot. In order to calculate the Carnot efficiency, we need to use, we just need to calculate the efficiency. So, and since we are talking about a cooling system, we use the coefficient of performance. So calculate this again of your refrigerator. And as we have already calculated here, I'm just going to use this. And this is Q cold, in. But as we're not talking about a work input anymore, we're just talking about the heat input, we have to express the work input in other terms. Well, and this can basically be done by looking at the system. I've got about the energy of the system. We have two energy flows. We have a flow out and a flow in. And I need to add energy to the system by work in to get this outflow of energy, the QH out. So my work input is actually a difference between the hot output of energy and the lower output of energy. So my work is defined as Q hot out minus Q cold in. And now it's just mathematics. I want to get rid of, well, actually I just want ones, to have ones in my equation, so I'm going to rewrite it. COP of a refrigeration cycle, and this is just so I'm going to divide everything by Q cold in, so it's 1 over QH out. And since I'm dividing by Q cold in, I have to divide this by Q cold in. And I have to divide this, which becomes 1 as well. So this is still the coefficient of performance. And when looking at a Carnot cycle, I can assume that the following statement is true. Q cold in over Q hot out is lower or equal to the temperature cold and the temperature high, the higher temperature. So I can assume that this ratio is true. So since I know that this statement holds for a Carnot cycle, I can determine my Carnot coefficient of performance now. So the coefficient of performance, Carnot, for a refrigeration cycle is defined as 1 over T high divided by T cold minus 1. So here we have our Carnot coefficient of performance, which actually is the most efficient case we can have for a cooling cycle. So now I've erased the board, I'm going to draw the TS diagram of a refrigeration cycle, and I'm going to point out which difference may arise due to the refrigeration cycle not being an isentropic, not an ideal cycle. So let's look over here. So the TS diagram, temperature, entropy, and over here the vapor dome, and now I'm going to draw the cycle. And well, I'm going to start at point 4. So after the throttling valve, and that will be about here, point 4. And from point 4 we'll go isobaric. Isobaric, not really. In an evaporator is usually a set of tubes, and this set of tubes, of course, they have friction and resistance and whatever. So there will always be a bit of pressure loss in my evaporator. So let's indicate that the pressure drops slightly. Yeah, so the pressure will change. And one of the difference between an ideal cycle and a real cycle may be that we end a little higher in the vapor dome. So while evaporating, my fluid may become a little more, how do you call it, superheated. So we may have a superheated vapor. Well, of course, in a real cycle, the compressor won't be isentropic, so we'll have a bit of a bend in our curve, whereas in an ideal cycle, of course, this is isentropic. So this will be point 1. This will be point 2 actual. This will be point 2 in an isentropic state, and it will look like this. So, just to describe the things that may happen here, we might have a superheated vapor, and just not the saturated vapor but superheated. Over here we have, of course, isentropic versus a real compression. So that may be a difference between the real cycle and the not real cycle, the ideal cycle. And over here we may experience the same when going through the condenser. Condenser is usually a set of tubes as well, so you have a little bit of pressure drop. Maybe up here, and sometimes the fluid is even more cooled than just to the liquid line, than the saturated liquid. So the fluid may become a compressed liquid. Point 3 over here, and from there we go back again to point 4, isentropic. Of course, isentropic in real life is probably not isentropic. It will always require some energy, but these differences will probably be negligible. So we have the flow going this direction. So over here again, and over there as well, I'm going to indicate pressure drop due to friction in the pipes. Friction. And over here we may have a subcooled liquid. So these are a couple of differences between the real and the ideal cycle. Of course there are more, but most of them are negligible for the level of well, the depth of knowledge required for this course in thermodynamics. But it's always very wise to keep them in mind. So more examples of refrigeration cycles are stated in the lecture slides about lecture 13. In this lecture, some things are taught about, well, imagine you have a refrigerator with a freezer compartment as well. Then you have a two-stage refrigeration cycle, cooling cycle. So how does this look like? That's stated in the sheet, so it's wise to have a look at the sheets. Over there you can see some slides about cooling using a Brayton cycle, or for instance a turbojet engine to cool, so how cooling is actually done in airplanes. There's also something about cooling by solar power, and these are just slides you can easily click through, so it's wise to have a look at them. In the next video, which will be a short one, I will tell you something about heat pumps. So I hope to see you in the next video. Thanks for watching.